Now let's work on statistical inference, since the estimation of the model is over. We click on Results in the menu window, select the SPM file, click Done. This opens Contrast Manager. This is a very important step. If the contrasts are not defined in advance, we'll have to do it here. We use the button to define new contrast. Here we see a very simple design. As you remember, we have only one condition, the alternation between the listening and the rest. There are two types of contrast. In detail, we will discuss them later. But we can easily get the main idea at this level, even with only one condition. There can be T contrast and F contrast. Those are two alternative approaches. T contrast is able to detect the effect in one direction. For example, during the active condition, the activity is higher or is lower than during the rest. First, we indicate the name of the contrast. For the situation when the listening gives greater activation than rest. The name can be changed. It is pretty arbitrary. You can call it whatever you want. But the contrast vector is something very specific. In our case, we have just two options, either +1 or -1. For listening more than rest, we enter +1. After we click Submit, and this is how this contrast vector will be graphically represented. A gray bar oriented upwards. We click OK, and then we define new contrast, which is rest more than this. What does it mean? Let's imagine that during listening, somewhere in the brain, the activity will be reduced. The neuronal activity will be reduced, and this will end with a reduction of the signal, the reduction of the bold blood oxygenation level dependent contrast, which is roughly equivalent to the blood flow. So that we are able to identify such areas, we enter contrast -1. We click submit. Now we see the gray bar turned downwards at the top of the condition of interest. This is the baseline mean contrast, and typically we never manipulate with it because all the fMRI designs deal with relative alternation, not the absolute signal which is encoded here. We are not interested in the absolute signal intensity. We are interested in the alternation of the signal intensity, which is statistically explained, statistically linked to the condition of interest, which is called a regressor of interest otherwise. And this is what is called contrast. We have one contrast for positive response to listening and other contrast for negative response to listening. But we can also create an F contrast. F contrasts are very different than T. Such contrasts are sensitive to any kind of changes, either the increase or the decrease. This makes it more sensitive to detect any changes, but at the same time less specific, less hypothesis driven. And here we can enter either 1 or -1. It doesn't matter at all, because the sign is not detected by this contrast. Whatever happens will be detected. And as you see, the shape of the representation is different. Now it is just a white rectangle at the top of the condition which we try to explain with this contrast. We click OK, and now we have 1 F contrast and 2 T contrasts. Let's select the first one and click Done. I just verify that we follow the instructions. And this is where we go next. We go to the result assessment. Very important part. We apply no masking. We select family-wise error adjustment. I will tell you a bit later what it is. The p-value is by default 0.5. Click enter. Press enter. And no extend threshold 0. And you press enter. Here what you have. This is the result of the statistical analysis. What can we see in this figure? First of all, we see the glass brain. Here you see the contour of the horizontal plane, sagittal plane, and coronal plane. And here is black or gray the areas where the activity changes according to this contrast is highlighted. We have some bilateral activation in about superior temporal lobes. And here you have the table. We will discuss this table a bit later. Let's look at this window and let's see what are the useful functions in the interactive window. The most useful are the contrasts, where you can pick one of the pre-generated contrasts. The plot, you can plot the fitted response. Whole brain current cluster allows you to navigate between different sets of statistical results. If you can include in the table the whole brain, all the results, or just the current area where the cursor is located. I will explain you how to navigate a bit later. It's very beautiful and interesting. Overlays allows you to map your statistical results in the shape of colorful blobs onto the anatomic image, which gives you very beautiful and attractive illustration and allows you to further navigate your results and study the anatomy of your responses. In the figure window, you have a nice trick to move the result table, which is perhaps the most important part of your results. Surprisingly, this is even more important than the image. You go to SPM figure, you click result table, and this will generate another window where you can display the table, while this part of the graphic window will be used for something else. The next thing we have to discuss is the table. So let's go to interactive window and click on the whole brain once again so that we see the table in a separate window. This table includes a lot of different parameters, and this table is useful for navigation across your results. Let's start from the very right part of the table. Here you have coordinates in millimeters in the MNI system. If you remember, MNI is Montreal Neurological Institution template, a standard canonical template toward which we have normalized our functional and structural data. X means right-left axis, Y is anterior-posterior, and Z is top-bottom. The zero reference point is, as you remember, anterior commissure. If you click on the coordinate, let's select the first one in the table. The cursor in the arrow cursor in the glass brain will automatically go to this spot. And this coordinate will be highlighted in red. So what means this coordinate row? This is the coordinate of the highest peak of the statistical image. This is a very important concept. Our functional images have a number of voxels. At the bottom of the table you can see the total number of the voxels. It is huge. About 2 million. Here you see the voxel size, 3 by 3 by 3 millimeter. If you remember, this is what we defined in our normalization procedure. Every voxel has its time series of the intensity of the signal and when we compare this time series with the regressor, statistical analysis estimates for this particular contrast the value of the Ttest. This is well-known statistical parameter. But we have about 2 million of those values. And those values are arranged in a 3D volume. Absolutely similar to the image, the functional image. And the program is able to separate those voxels where the level of statistical index is higher than the threshold. And this is where the threshold is precisely indicated. It is 5.2. For this level of statistical significance. This is surprisingly high. Typically, Student test statistics give significant results at 2.3 or something like this. Why is it so high here? Because of those letters which are shown in the brackets. Family-wise error. What does it mean? And how to find it in the table? Very simple. This is the result of the Ttest in the voxel, which is located here. This is the maximum t-score. And here in this column you see P, family-wise error corrected. Here you have P uncorrected. You see all of them are just 0 here. But the first line, well, this is the most strong signal. It is 0 on the left as well. But if we look at those, we see that they are just above the threshold of 0.05. And this is what we asked for. You remember? We selected family-wise error corrected statistics at this significance threshold. So, the corrected p-value is always smaller than uncorrected. For what do we correct? We correct for multiple comparisons. Why do we need to correct for multiple comparisons or multiple measures? Because we have this huge number of the voxels. Imagine that out of 2 million of voxels, you have 5% of voxels where the statistical score is significant just by chance, which corresponds to this level of significance, 0.05, 5%. The 5% of 2 million is I guess 10,000 of voxels. Excuse me please, this is in millimeters and this is in voxels. Anyway, out of 100,000 voxels, 5% gives you anyway 5,000 voxels, which is a lot. That is why uncorrected statistical scores are just unacceptable and give you too high chance to get false positive. You find a statistically significant response where it is actually just by chance because of the random fluctuations of the data. This score takes into account several things. First, the number of the voxels, then the distance between the voxels and the shape of the structure. If two voxels are located far away from each other, they are considered to be independent. If they are close to each other, they are not independent, and we don't have to to increase the threshold so much. If the smoothing of our data is smaller, then we have to correct more for the whole volume of the brain. If we smooth more, we correct less, and the difference between the corrected threshold and uncorrected threshold is smaller. All this is about the peak, the maximum statistical score across the volume, where a lot of voxels are grouped together. Each voxel has its own peak level statistics. But in addition to peak level, we have cluster level statistics. This is quite a different approach. If here we rely on the t-score, here we rely on the number of voxels in the cluster. Again, cluster is the agglomeration of the voxels. In this cluster we have 482 voxels. A lot, but in this cluster we have even more. We have 816 voxels. And independent of those statistical results, we have separate statistical score, both uncorrected and corrected, for the cluster level results. However, the conclusion from peak level and cluster level is a bit different. If we have a peak level significance, we can say that in this particular coordinate we have significant activation. If we have only cluster level significance, at the moment it is impossible because we have a threshold that will include only peak level significant results. But let's imagine that some of those are not significant. Non-significant voxels can group together and create a significant cluster. Significant cluster is a cluster that is big enough so that we cannot imagine that it appears purely by chance. It's another statistical estimation. So if the peak level is non-significant but cluster level is significant, we say that we don't know in which coordinate precisely do we have a significant activation. But we can say that in this part of the brain, roughly, let's say occipital cortex or hippocampus, whatever you see in your map, you have a significant cluster. It is less precise, but typically cluster level statistics seem to be more sensitive to detect small but significant responses in the fMRI. The next thing I wanted to show you is how to plot the fitted responses. We select one of the significant pixels. We click on plot, select fitted responses, the first contrast listing more than rest. We click on predicted and plot against scan or time. And this is what we get. The gray line shows what do you expect. This is your model. And the red dots show you your model plus error. You see, the correspondence is not quite accurate, but it is absolutely clear that we have alternations of the signal in this particular voxel which correspond to the structure of our experiment. Let's take one of the voxels with smaller significance, and you see that the noise is much bigger in this situation. And the last thing we need to see is how to build an overlay. We select sections, we go to structural and take normalized structural image. This is where we want to plot our statistical results. We will see statistical image at the top of the anatomical image. In this situation we can easily identify the anatomy of our cerebral activation. And here it is. You can see that the crosshair is located at this specific coordinate because we select it in our table. But if we go to other location from the table, the crosshair will automatically move to this location, both in the anatomical overlay and the glass brain. There's another way to try to identify the anatomy. Here in the atlas, in the interactive window, you can click label using and neuromorphometrics. It is a new feature of SPM. It takes time to estimate, but at the end, if you right click over the coordinate, it gives you the list of the brain areas with different chances, different probability that this given voxel is a part of this structure. Right parietal temporal sulcus percaps, planum temporale 31%, but also quite high chances that it is a part of white matter and central operculum. Operculum is the cortical area in between the insula, which is inside, and whatever it is in the surrounding, the temporal lobe, the parietal lobe, or the frontal lobe. This is called operculum. For other anatomical location, you see different identified brain area. Quite high chance that it is unknown. It is just at the border of the brain, so maybe it is not a part of the brain. Left precentral gyrus, most likely. You have some tiny motor activation at the time of the listening of the words. Interesting. And it is quite significant here, but just at the individual level. I don't know if this activation will survive at the second level of statistical analysis, when you summarize the statistical contrast data from several subjects. At the very end, I propose you to look at other contrasts we identify. Rest against listening, where the rest gives more activation than the listening. We don't know if it is the rest that activates the brain or it is the listening that will suppress the cerebral activity. We have just few voxels. Here what we can do is to change the threshold, to make it more liberal. This is more liberal threshold 0.001, but uncorrected. This is typically not significant, but it gives much more clusters. And the cluster can be significant. Here what we see is some cluster, non-significant at the peak level. This is the most significant peak, and it is still non-significant. But the cluster is big. It is 61 voxels together, and the cluster level is quite significant. We go to overlays to see our beautiful image. Over the anatomy, we click previous sections. It will automatically select what you have used before. Beautiful. This is posterior cingulate, and this is ventromedial prefrontal. Those two are parts of the default mode network. It is a very specific and quite mysterious set of cerebral areas. They tend to be task negative, which means that they are less activated at the task, whatever is the task, than during the rest. And we see that the activity is greater in this area during the rest in comparison to the listening task. We can plot fitted responses from this area. We select rest more than listening, predicted, scan our time, and here is what we have. Quite noisy. That is why it is not very significant at the peak level. But the cluster is big enough, and we consider it a significant statistical result. We can select the third contrast so that you see the difference of F contrast from the T contrast. In this image, you see everything. Some clusters respond to the task in a negative way, and some in positive. In total, there is more activation. How to identify the direction of the response, if it is positive or negative? Here you have no idea. Here, no idea either. There is a simple trick. You click plot, you select contrast estimates, and you select the right contrast, which is F contrast. The response is positive here. Let's try some area where the response is most likely negative. Here, you remember that it was some kind of task negative. How to select this cluster and to see where is the peak, the maximum of this cluster? You click button current cluster, and you see in the table statistics just for this cluster. There are more than 5 voxels there, of course. There are 110 voxels. But here you see just 5 values. Those are separated with at least 8 millimeters. This is how it works in SP. But let's go to the peak. And let's click to the plot and identify the direction of the response. We click on listening F contrast, and you see, as expected, the response is negative. I hope my explanations today, yes, this is what we have already done. I hope that my explanations today were clear enough. If they were not clear, please don't hesitate to forward me your questions. Thank you so much for your time and your interest, and good luck.